So, stereoisomerisms, there are two classes as I already said. Stereoisomerism, there are two classes. One is we have geometrical isomers, one more is we have optical, right? Geometrical and optical isomers. So we'll take like this, students. We'll have tetrahedral complex, octahedral complex and square planar complex, right? So we'll take like this. Just to give a primary, the basic hint regarding how it goes, we'll take geometrical isomers, geometrical and optical, right? Geometrical and optical, make it clear. Tetrahedral complex, no geometrical isomers possible, we'll put it across by. Optical isomers, yes, it may be possible for the tetrahedral complex, optical isomers may be possible. So octahedral complex, both geometrical as well as opticals are possible. Square planar complex, geometrical isomerism is possible, where the optical isomer is not possible. This particular, the table, you just keep it in mind, students, could be required. Okay, you have a tetrahedral complex. If you are having tetrahedral complex, if they are asking how many geometrical isomers are possible, no geometrical possible, optical possible depending on the condition. Again, octahedral complex can have geometrical as well as optical can have. Okay, square planar, geometrical possible but not the optical. So we'll go for the first thing, tetrahedral and the square planar complex, which is easy to predict the geometrical and the optical isomers, how it goes. Then we'll go for the octahedral complex in detail. First one is we'll go for the geometrical isomers. The square planar complex. Square planar complex. See, we know the condition to be satisfied for showing the geometrical isomerism is, and also the optical isomers. See, for showing the geometrical isomers, the condition is there should be opposite side should be there. So if you are having a square plane, if you are having a square, this is opposite to this. That means the 180 degree angle we have, right? So the one angle is 180 degree and this angle is 90 degree, right? So there is a 90 degree bond angle and 180 degree bond angle. There is a 90 degree bond angle and 180 degree bond angle. And hence, this form we referred it as a transform opposite side, and the adjacent side is what we referred it as a cis form. Clear? We'll repeat again. In the square planar complex, geometrical isomerism is possible because it satisfies the condition. That is, you have two different sides. That is, one is adjacent side is there, another one is opposite side. One is 180 degree, another one is 90 degree. For example, if you are having a metal ion at the center, A, B and C and D. Right? A, B, C and D. So I can write it as, in one case, the A and B are at the adjacent side, I can write it. In the second case, I can write A and B are at the opposite side. Right? A and B are at the opposite side. In this case, A and B are adjacent side. The angle between A and B are 90 degree, and in this case the angle between the A and B are 180 degree. That is why the geometrical isomerism is possible in the square planar complex. Okay, condition to show the the square planar complexes, there should be opposite side. Otherwise the geometrical isomerism is not possible. Condition to show the geometrical isomerism is there should be opposite side. Otherwise the geometrical isomerism is not possible. As far as geometrical is over, condition. As far as the optical is considered, student, there should not be any plane of symmetry. Any symmetry should not be there. It can be center of symmetry or plane of symmetry. Symmetry of the system should not be there. System should not show the symmetry. System should not show the symmetry. So if you consider the square planar complex, right, there is a plane of symmetry. Because the fact that it is a square planar, there is a plane of symmetry. Because if you keep a mirror in this plane, the opposite side, both the sides are same. It will be a mirror image, right? So that is the front and the back side, you don't have anything. I mean, you have a plane here in the system, and hence there is a plane of symmetry in the square planar complex. Name itself indicates it's a square planar complex. Since there is a plane of symmetry, square planar complex cannot show square planar complex cannot show geometrical isomerism. Geometrical isomerism. Why it is not showing geometrical isomerism? Because there is a plane of symmetry in the system. They may ask you why it doesn't show. It doesn't show because there is a plane of symmetry in the system. Plane of symmetry in the system. Clear? So now let us now move on to the geometrical isomerism in the square planar complex. Anyhow, we have concluded that in the square planar complex, optical isomerism is not possible. If at all they are giving, for example, nickel tetracyanide complex, if at all they had given, platinum tetrachloro complex, if at all they had given, these are all square planar complex. And if at all they are asking how many optical isomers are possible, no optical isomers are possible, because there is no question of the optical isomerism, because there is no opposite side in the tetrahedron. All are 109 degree 28 minutes bond angle, no opposite side is there. So there is no question of the existence of the optical isomerism in the optical isomerism in the square planar complex. So, but the square planar complex will be possessing geometrical isomerism. Let us take few of the square planar complex. For instance, I will take MA4. MA4 is the first square planar complex I am taking. You can write it like this. You will be writing like this. That means you cannot get one more form. Right? All are same, all the ligands are same. So MA4 will not show the geometrical isomerism. I will take MA3B. Can it show the geometrical isomerism? This also cannot show, because I will write it like this, student. B, A and A. Right? In this case, one of the A is opposite to the B. Right? So now one more form you cannot write it, because B, if I am writing, if I am keeping the B here, again B is opposite to A. Right? So all A are same. All A are same, right? Because the nature wise all the ligands are same. So and hence I cannot write two different isomers. Both the isomers are same. In this case also B is opposite to A, this A, and two more A it is adjacent to. In this case also two more A it is adjacent to, one A it is opposite to. So both the forms are same. And hence again MA3B complex also the geometrical isomers are not possible. In the square planar complex, if it is MA3B, then also you cannot have a geometrical isomerism. Let us take for example MA2B2. Can the geometrical isomerism possible? Yes, because I can write it as students MAABB like this. In this case, what is happening is these two are adjacent side, at the adjacent side. In one another case, I will put it like this, B at the opposite side. So just check. See, two B atoms are at the adjacent side. The bond angle is 90 degree here. How about the bond angle between these two? It is 180 degree. Right? It is 180 degree. Or in other words, the complexes M of the type MA2B2 does show geometrical isomerism. How many geometrical isomers are possible? If at all they are asking, only two forms possible. We cannot write three forms, right? So MA2B2 does show the geometrical isomerism. I will take one more example. MABCD. One more, the kind of square planar complex. I will take it. MABCD. It may be like nickel, cyanide, right, Cl, Br, Co. This can be done. For example, I am putting like this, or else it can be a platinum. For make it easy, if it is a platinum, you can take, the different also. You can take iodine also here. Doesn't matter. Platinum will always be having D8 system. It will always be showing geometrical isomerism D8 system. This is the example if they had given and asked you to predict whether it shows geometrical isomerism or not. Yes, it shows geometrical isomerism. Question is how many geometrical isomers are formed. So M, A, B, C, D. M is at the center, right? I'll put it A, B, C and D. This is the one form. Second form I can write it as M, A I'll keep it as such, B I'll turn around, C and D I'll put it. Third form I can write it, students, M I'll keep it as such, M, A and D I'll keep it here and it is C and D. Sorry, C and D. So, or in other words, only three forms are possible. Any other modification if you make, you will not be getting. I will repeat again. In first case, A is opposite to C. In the second case, A is opposite to B, and third case, A is opposite to D. Automatically, rest of the forms will be fixed. That is, it can form 3 geometrical isomers. If at all they are asking how many geometrical isomers can be observed in the case of, the square planar complex having M, A, B, C, D. Square planar complex having M, A, B, C, D. It can show 3 geometrical isomers. One case A is opposite to C, another case A is opposite to B, another case A is opposite to D. Rest of all forms, whatever the modification you do, you will be getting the same form. You will be getting same thing. So, no variation will happen, students. Okay, so this is M, A, B, C, D form, M, A2, B2 and also M rest of the things, I mean the M, A2, B2 and M, A, B, C, D are the 2 forms which can show the geometrical isomerism from the square planar side.